Okay, so for sensor we need to define the terms which are commonly come in the specifications. When we see any particular sensor, we come across some terms, and that actually help us to decide what type of sensor we will use. Okay. So sensor is very important. As we know, the sensor will be one of the fundamental elements for any system. We need sensor for any system whenever we think of any kind of system. So the sensor will be depends on the what system we are going to make. So it gives us either temperature or humidity, whatever it is. So we have many parameters, and that sense comes from the sensor, and then we have the signal conditioning circuits. Finally it goes to the processor, and the processor gives you some kind of information, whether you want to display it, whether you want to use it to control. So that's the parameter it goes. So effectively, if you think of whole smart sensor, we get inputs from the sensor, we give output for controlling something. So in terms of the characteristics, there are many characteristics. Actually, I was listening to the lecture Professor Islam just gave. You have seen some of the terms, so which we will be again repeating. So some of the characteristics become very important. Some of the characteristics is like a part of the system which may not be so important. So one of the things which we will be, actually two things which we will be very much concerned is the sensitivity and the selectivity. So we will be talking that too, but there are many other terms which we need to study, especially when you buy a new sensor and you use it for your applications. First thing what you need to do is to characterization of the sensor. Okay? So the characterization of the sensor is basically you need to know how is the output of the sensor with the parameters you change. So you measure something with the change of that parameters, how your output is coming, because you need to know the relationship, and that will be useful for the measurement. So we will see the static characteristics as well as dynamic characteristics. Sometimes in order to do that, for test sample we give some input, make the input constant, and we see the output. So that tells us that how much time the sensor takes. So even though you give some static input, but the response of the sensor will not be instantaneous. It takes some time. It may take some kind of characteristics which slowly changing, and then it becomes steady. So we have to know all these things, especially for the gas sensing applications. You will always find that it does not give you response very quickly. There is always a delay, and if the gas intensity or gas concentration changes very quickly, then you will have some problem if you have too much delay. But we need to know the sensor characteristics so that we can tell about the. So the static characteristics means your input is constant. Ideally it never happens, but you can assume that in the laboratory environment. Dynamic characteristics, input is actually changing all the time. So these are the two main things. So now we define the parameters of the specifications which comes in the sensor. So we all know the accuracy. Okay, we always say the accuracy. What is the accuracy of sensor? Sensor is accurate or not? What do we mean by that? Okay, and you will find the terms gives in terms of percentage, whether plus minus 1%, plus minus 5%, plus minus 10%. So what do we mean by that? So you want to get a certain output, which is the ideal output, okay? But you get some other output. So you compare with the two output, and it always gives you percentage. So the percentage value is sometimes very, very important. As you know, that percentage means there is something in the denominator. If you make the denominator bigger, your percentage always becomes less. So sometimes you may say that the manufacturer gives you different range. Okay? And if the range is very high, then you can actually make the accuracy very good. But you cannot do that, because if you say you want to measure 1 volt and you are measuring in the form of 100 volt scale, your denominator becomes 100, but it's not the correct, because 1 volt, in order to get more accuracy, you have to go for the other range. So that type of thing, sometimes it can be play around. So manufacturer can play around, but as engineers we need to know what exactly we mean by that. Okay? So let us say that we use a pressure sensor. It operates in the range of 0 to 1 bar, and we say it's plus minus 0.5% accurate. So what it means that we need to accept some error. Okay, so that error we can calculate 5% accurate, so plus minus 0.05 bar. That's the absolute value you have to take. So you know what is the ideal value you should get. You measure. If it is within that, the difference of that within that, then you say it's fine. But if it is outside the range, then actually the accuracy, what they are telling, plus minus 5%, is not the correct. Okay, they are actually bluffing something else, which is not the correct value. It's clear, isn't it? So the accuracy actually is related to the scale. Okay, so it's related to the scale. If sometimes you say it's 0.1, its error is 0.1 something, 0.1 degree centigrade, but that may not actually tells you the real picture, because you may have 0.1 degree centigrade in some applications good, but you may not have that good value in some different other applications. You understand? So the real value may not give the correct picture. So you need to see the percentage. So another thing is the static characteristic. Let's run an example. So we take the range 10 bar and we get the error 0.15 bar. So how do we calculate the accuracy? And if the maximum reading change to 2 bar, what will change? So error is 0.15 and range is 10 in the first case. So your accuracy becomes 1.5%. So the error divided by the maximum. So if you make the range 2 bar, same error 0.15, your accuracy becomes 7.5%. Of course, from manufacturer point of view, you can always sell 1.5% error. But if it is 7.5% error, you actually make many people discouraged, isn't it? Because it's too high. So it's the same equipment, same sensor. It's just you change the range. You understand? So sometimes you may actually go for this by increasing your range to make people fool. Clear? So that's one of the example what we can tell accuracy, but it's a different figure. One case acceptable, another case completely unacceptable. So just another example. So pressure gauge sensor, their accuracy plus minus 0.5%. One has a range 1 bar, 0 to 1 bar, another has a range 0 to 10 bar. So if you measure 0.9 bar, which one is suitable for your applications? So two equipment, you are measuring one particular parameter, but different range. Okay? So always, like if I have 2 students, I can give 2 instruments. Okay, bring me the result. You understand? One gets very good accuracy, another is, they are not fault. And I can tell the fellow who came with lot of error, useless guy, doesn't know anything. You understand? So it's just the representation of parameter. Okay? So when I will give you the last lecture, or not the lecture, the paper writing, you will see that how impact factor is calculated to fool the people of the whole world. Okay? Because we can make the denominator very low or denominator very high to make the impact factor high or low. So if you want to go for the 0.9 bar, you will see here the situation become, so what actually, so in this case your accuracy become, for 2 different scenario, accuracy become 0.05 bar, and that gives you 5.6%, but in other case you will find that it becomes 55%. Okay? So completely different representation. And that's what actually, if you remember yesterday we were taking the data presentation, effective data presentation. It's one of the art. Okay? Some people can present the same data in a completely different way. It's all about presentation. How do you define somebody is smart? It's the art, isn't it? Okay, so next one is confusing one, is called precision. So accuracy, you all know that, okay, what is my ideal value? What we are getting from the measurement, we just take the error and represent as a percentage. But how do you define then precision? Okay, so precision and accuracy, they are related but not related. So we can say the equipment is precise, sensor is very precise, but not very accurate. Okay? So if you see the definition, is the capability to give us the same reading when you do many times. Okay? You do repetitive experiment. I mean, one of the things when we think of journal publications, you need to have that you cannot say, I have done only one time. No, reader will not be very happy. So you need to say that we have repeated the experiment either 3 times or 5 times, taken the average reading. Some other journal, they like to see some kind of statistical analysis. And whenever it's statistical analysis, as you know, actually I feel very, very different, because in India, especially in Jadavpur University, we did not study any statistics subject. But in New Zealand, in the undergraduate first year, you have to do one paper on statistics. Because if you do research on agriculture, as you can know, the soil here and soil there, no relationship, isn't it? So you cannot have actually absolute kind of things. So statistics is very important. And in research, statistics is really, really important. So you can always say mean, median, all this way. So that's really important. So if you want to do statistical analysis, you have to do many times, because you do not get the same result every time you do. If you get it, you can be lucky, but in general you don't get. So you will, if you say the dictionary precision, you can say the state being precise or exact. Okay? So ability of a measurement to be reproduced consistently. So you get consistent result. So that's the precision. So it's just difficult to give you in terms of the text. So it's just in the graphical form. We want to measure within this circle. That's the true value. But here, if you see this situation, high accuracy, high precision. So if you get within the circle, your results is accurate, your results are precise. Come here. You are getting, if you say absolute result, okay, absolute value of error, maybe okay, but you do not get within that, isn't it? You do not get within that. Here, both are not valid. Clear? So here your accuracy is low, but precise, because you are getting consistent result. You understand? You may not get the accuracy, but you are getting, every time you do, you get the same error maybe, but you are getting the same result. So you can say that I'm getting the same result, so it's actually precise. It may not be accurate. Understand? But here, here, the third case, your accuracy also changing, and you are not getting repetitive. So if somebody asks you which one is best, of course you will tell this is the best. But out of these two, it depends on whether somebody is looking for the precision, somebody is looking for the accuracy. In fact, maybe this one, you get accuracy maybe good, it may be a little bit higher than the, but if you say precision, it's not, it's giving something, 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 something. Okay? So sometimes it's a little bit confusing, but precision effectively means, I mean, some books maybe don't say precision, they may say repeatability. Okay? That's the term they use, the repeatability, okay? Which is quite common. So here we do some experiment. And we always get, we always repeat something, and you know this is not correct. You know this is not correct. So that's the situation you will have. So you are having some systematic error inside the system which you cannot eliminate. Okay? So that type of things come if you deal with the magnetic sensor. And magnetic sensor, the bias, magnetic bias is very, very important. And if you biased in such a way that you really don't know how much you actually biased, it can give you that type of situation, that the effect of the bias is something which is beyond your control. Okay? So you always get same result, and you are 100% sure that no, this is not the correct, something is going wrong, but you don't know where. Okay? So you ended up this type of problem. So sometimes you actually use in the bell-shaped way of representing. So you can see here, if you get very close to here, then you can say your result is quite accurate, isn't it? But in terms of mathematics, if you say the precision, you actually need to define standard deviations. I mean, standard deviation is not a term used by the engineers so often, isn't it? It's by the statistics people. They always, they don't use that way we say. They always go for the standard deviations, mean, norm, and so other things. So if the standard deviation is small, then you can tell this is precise. And the standard deviation, you know how to calculate. Like you have to mean value, then actual value, take the difference, take the square, add them, and divide by, if you have n sample, divide by n minus 1 and square root. So that's why it's little bit mathematical things. But if the standard deviation is small, you can say it's precise. If the value is close to the mean, you can say it's accurate. Now we'll take few terms of the static characteristics. Okay? So one of the term is used, tolerance. So tolerance is like how much you can tolerate, isn't it? I mean, it's very similar for the instrument. So how much you can allow your instrument to give error. Okay? So if you think of percentage, percentage actually may not be appropriate. Percentage may not be appropriate because percentage changes with your range. But in some situation, you actually rely on the absolute value. So for example, if you think of body temperature, we all know the body temperature varies between 36 to 39. Okay? I mean, it's not that much, but it's like 36.5 to 38.5. There, 0.1 degree centigrade error, we always think that way. We never actually come percentage when doctor measure the body temperature, isn't it? Have you heard anyone that, oh, you have got 10% error in your body temperature? No, it's something like 0.1. So some places, actually absolute value gives better representation than the percentage value. So the tolerance comes there. So you may have the maximum error which is defined by the percentage, but when you accept the things, it comes to tolerance. So another important thing is the range. So range is also something which actually you need to know what you are measuring. Instrument can give the capability of a very high value to a very low value. But if you express that as the error, you always get very good error because your denominator is too high, isn't it? So you will again come to the different situation. So the range is more important in the specifications. But you should not be looking only the specifications. Okay? So if you want to see the accuracy, you will never ever get similar accuracy for the whole range. And that's why always you will find the range is divided into smaller range. So for voltage measurement, you will see that if you want to measure 500 volt, you never go in one range. You may have like multimeter, digital multimeter. Why do you actually change? Because we change the range so that you get better resolution. Okay? So that also related to the measurement because you use analog to digital converter and you cannot use the same range. for the 12-bit, keeping them constant. So the range is the minimum value to maximum value. So it's the maximum value minus minimum value. That's the range in our case. Another thing is that bias. So the biasness is not related to all types of sensor. It comes to some specific sensor. Okay, some specific sensor you need a biasing things for its operations, but it may not be useful for other. Like if you think of the Hall effect sensor. Hall effect sensor, you actually have a magnetic field. Okay, and then if you one side of coil you apply some magnetic field, and then if you apply current in another axis, you can get some voltage, isn't it? So that type of situation, if you do not use the biasing field, the Hall effect sensor doesn't work. But it doesn't matter for other types of sensor. So it's actually that biasing things can be producing some error. You understand? So for example, if you take the again Hall effect sensor, you assume that B, so it's like if you say voltage is actually Bi something, okay? Some constant, Hall effect constant. So if you say that B is constant, so then the output will be only changing with the measurement, which is the current. But how do you ensure that is constant? So that can change and that can produce some error. So sometimes it's very important to know that what is the bias. Linearity, what Professor Islam actually told in his class, linearity, always think of that when we measure something, output which we express in the y-axis and the input which is our measurement along the x-axis, and we get a linear characteristics. But never ever you get linear. Okay? Never ever you get linear. Nothing is linear in our life. Everything is non-linear. So always you come to the question, how can we linearize? And earlier days, before the microcontroller programming, all this came, in fact, I remember in 80s, there was a book, 900 pages book on the linearization technique. Okay? I think that book you don't see anymore, because now always people use for software to linearize the things. And the best way of doing that is the piecewise linearization, because straight line is the most important linear characteristics. Okay? So you need 2 points, just draw a straight line, very simple. Okay? Then of course you can go to parabola, or you can go 3rd degree, 4th degree, doesn't matter, and there are many techniques. Okay? Newton, Raphson, and go on and on. But the best one is the straight line. So piecewise linearization is basically you are splitting into 2 points, straight line. And if you do microcontroller based system, that's the best, and you get very good accuracy. So how much close they are, that can dictate the accuracy level. And if you see in terms of the implementation, straight line is the best, because you have only one multiplication. You understand? But if you go for 2nd degree, if you go for 3rd degree, your multiplication becomes more. And one multiplication is actually more than 12 to 16 linear code. You understand? I mean, we always write the software, if you think of the high level language, it doesn't really matter. But at the end, it comes down to the machine language. And then how much is the execution time, that can be very, very important to decide. So we need to think of how we can actually use the logical and or add, logical operation and addition and subtraction. Because ultimately whatever it is, they implement using that. So that execution time depends. So the linearity need to express, it's also expressed as a percentage. How much is the deviations from ideal characteristics as a percentage of the actual value. So you do not use the range there or the full value there. So here you can see that we always think of a straight line between the measured quality and the output, and in this situation you can tell how much is the linearity. Also you can tell actually how much is the error, but telling error from the linear curve is no meaning, isn't it? Because they are different parameters you are measuring. Okay? So when we tell the percentage linearity is actually from the expected curve, how much is the error. And this is the most important one, sensitivity. So you want to use sensor to measure something, isn't it? So when we say how sensitive it is, that basically we want to tell whether it has the ability to measure. Okay? And I tell you, forget about everything. Two important parameters which you will be dealing with sensor, one is sensitivity and the second one is selectivity, which is slightly different than sensitivity. So we will come to that later on. So sensitivity means basically you can think of is like the first derivative. Okay? So you have one parameter which you are measuring, then you change your input parameter slightly. Because of that, your output is also changing. So what is the change of output? What is the change of input? Okay? That's the definition of sensitivity. Clear? Now many people define in different ways. And sometimes if you have something in your mind and you do not want to listen what actually the author or others are telling, you may end up with some different idea. You understand? But usually the sensitivity, it means what is your input parameter. Due to the change of that input parameter, what is the change of the output parameter? So change of output as a ratio of change of input. So we can define sensitivity for anything. So for example, if you say the temperature sensor should be sensitive to temperature, but we can also define the sensitivity of temperature sensor to humidity, okay, or to pressure. So it's not that temperature sensor will be sensitive only to temperature. That's the ideal thing. You understand? That we can say, oh, it does not really care. But in ideal practice, it's not, because it's dependent on the environment. You can change the temperature sensor signal due to the change of humidity, due to the change of pressure, due to the change of any other operating conditions. Okay? So you can define that, but while you define, you should not define only the sensitivity. So if you say the sensitivity of the temperature sensor to pressure, you can tell that way. Sensitivity of the temperature sensor to humidity. Just if you say just sensitivity, you are in trouble. Do you get the clear idea? Sensitivity, it is always the ratio between the output and input. So change of output, change of input. But you can also define sensitivity, the sensitivity of this sensor due to this. That parameter, that text should be there. Otherwise, you will confuse. Clear? So one will be the main sensitivity, which is the ratio of output to input, but you can also define the sensitivity due to some other parameters. Okay, so usually we think the parameters which we are measuring and output. So here three different characteristics. Okay, so if, as you say, it's basically the derivative. So delta y by delta x. So if the delta y is more, you get more output. You can always say it's more sensitive. Okay, so in these three different cases, this one with the highest slope is the most sensitive sensor you have. So next one is that in different situations we come across different elements in between. And when we talk about the sensitivity, we may have sensitivity of one element, but in a system you have the combined sensitivity. So sensitivity, they are product of the sensitivity of each and every element coming in the steps. So if you see, sometimes if one of the element has got very low sensitivity, that can be reflected in the overall system. You understand what I mean? So you may have used a very good sensor which gives you highest sensitivity available, but then in your circuit you use some other element, and people actually don't care what is the sensitivity of your sensor because they want to measure something. So they are actually concerned about the sensitivity of the whole system. So what is important here is the selection of the component. Okay? Selection of the component, you have to be very clever so that that does not actually make your system low sensitive. So that type of situation is very, very common, and we have to be careful. So that is one example to find the resultant sensitivity. So it's okay, you can follow. And you may have a situation that if you have a wide range, it may not be sensitive in the whole range in the same manner. So you can calculate how it is sensitive, whether you can have an approximate straight line for the whole range, or you have approximate straight line piecewise. And if you come across, you can use that particular sensor where you get high sensitivity, which may not be the whole range. You understand? So sometimes that way you need to go for that. So as we know, sensitivity is the delta output by delta input. So you can find out what is the sensitivity for this, and you can get the different values for the different range. We also be concerned about some sensor where the sensor does not give any response, okay? And that's the dead band. So in this band, you do not get any output, okay? So sometimes if you do not know the characteristics of the sensor and you are using in this zone and you are not getting any result, you can blame the sensor and you can throw the sensor or tell some bad words to the company, but that does not help because the sensor has got that type of characteristics. And in some situation, you actually need that type of sensor, isn't it? So for example, you have got some earlier days, some control before the PID control was used, some control of heater on and off. You have to add some components to get this type of characteristics, okay? But that's one of the requirement in some system. And then the resolution. Resolution is also very similar like the other term what we have used, but resolution is used when you have got interfacing electronics, especially like digital processor. So your sensor may be giving some response, continuous response, but when it go to analog to digital converter, then that value for a bit, that becomes very important. And that actually related to the resolution. So how actually minimum value you can measure. I mean not minimum value, basically change of minimum value, okay? So one step to other step, how much? In between is like a dead band, okay? So how much is that dead band? So if you go for many number of bits, you can reduce the dead band. So that's the resolution, and which is very, very important. So we do not actually tell resolution in terms of absolute value. We always know 8-bit, 10-bit, 12-bit, 16-bit, sometimes like that. So if your reference voltage is constant, when you increase the number of bit, you basically divide it, so 8-bit, 2 to the power 8, so 256, 10-bit, you go 512, 12-bit, like 2024, like that. So you increase your value, so the denominator goes high, resolution gets better and better. So sometimes it may be very useful if you use some kind of sensor which gives you very low value of change for measurement, okay? Then your resolution should be very high, otherwise you will not be able to measure. Another important thing is the threshold. Threshold actually may not be so much important from the sensor characteristics. It's useful when you make a system and you don't want to change anything unless you reach that certain value, okay? And threshold is very, very important when you make comparator, okay? So when you make comparator, you actually have some lower threshold and upper threshold, otherwise you will damage the comparator. Because if you do not have that, then its switch is acting very quickly and you go for on and off, and you can damage. So thresholding will be very important, that you want to act if the level goes beyond that and you come back. So thresholding, hysteresis, they are very, very related. So the change occurs only when something beyond something. So those are related to static characteristics. Few things are for dynamic characteristics. Most important thing for dynamic characteristics is settling time, basically settling time, or how quickly it responds. And it all depends on what type of system, whether type 1, type 2, okay? So then you will find that time constant and other things will come into picture. So the reference input which are used, one is very common, is a step input. Step input is the most commonly used, and also sometimes the ramp input, okay? There is another input also, but acceleration input, but that's not so common. And also in sine wave, you can use reference sine wave. So reference sine wave can be very useful. It's not for the response time, but it comes for the phase delay. Okay? So it's the frequency response analysis which is useful. So usually we want to know the transient response. We want the sensor to be very quick so that whenever there is any change, you can measure that change. You can measure only when the output is changed. So that is done by step input. So you give a step input, and so you give here, and then this is your input, and then you see due to this input how your output changes. And then you have so that's the step input, and that's another input, the ramp input, which you give as a continuous input, and you see the effect of this. And then this is the sine wave input. Actually, sine wave input is more so to study whether the system is linear. Okay? If the system is linear, you will find that output also will be the sine wave at the same frequency, only there will be a phase shift. But if the system is nonlinear, you don't know what you are going to get. Okay? Then you have to bring Fourier from his grave to analyze what are the components you have. So usually, if you have a nonlinear system, it's very difficult to analyze. Okay? So we can feel ourselves lucky if we have a linear system. But all the system what we see around us are nonlinear. Understand? So we have to use linearization, and that was one of the reasons we will find not today when we talk about the impedance spectroscopy. We actually assume the system is pseudo-linear, okay? Because of that nature, that we want sinusoidal response. Because of that, we have to make the assumption linear. So these are the things. So now, if I give a step input to my system, I don't expect that my output will be instantaneous. So there is a delay, system will change, and if it is a first order system, you will always define what is the time constant, and the time constant will tell you how much is the time it takes to settle down. It never ever settle down to 100%, isn't it? In practice, it never, because it will need to go infinite. But we are in hurry, isn't it? We never have so much time to wait. So we always take, whether it's the 4 time constant, 5 time constant, depends on how much error you allow. If you do not concern about accuracy, you can say best is the 3 time constant, where you reach 95%. Otherwise, you go for 4 time constant, you reach 98%. Or if you are having enough time, go for 5 time constant, you reach 99%. But you never ever reach 100%, because 100% you reach ideally when the time is infinite. So the first order system again is rarely you get in life. Okay? If you get first order system, you are really lucky. But you never get first order system. Many times we make a second order system by giving too much damping to make it first order. but usually we don't have first order. If you have first order, you have only the rise time. For the second order system, again, what type of damping you have got? Okay, there are three types of damping, and if you are unlucky, you may end up with underdamp. So they have you have a second order equation, s square plus 2 delta omega ns plus omega n square. That delta is very, very important. If the delta is less than 1, you are underdamped and you will be oscillating. But if you can make delta either 1 or higher, then you can bring the system as a first order. Okay? But you actually cannot do the way you want the delta. So sometimes you need to add extra circuit to do that. Okay? So in other situations, especially like mechanical situation, it becomes even complicated. Actually, we electrical engineers are very lucky. We can play around with op amp and other things. But mechanical engineers, they cannot have that type of opportunity. They have to use damper, which is quite big and expensive and also quite difficult to implement. But they do, especially like civil engineers. When you think of the big rise building, in Japan, they actually designed the high-rise building to be protective from the earthquake. The damping is very, very important because every structure has a natural damping constant, okay? Natural frequency of oscillation. And if the vibration and the natural frequency of oscillation, they synchronize, you are gone. You cannot control the vibration. So they make two structures to control the natural frequency of oscillations. So when the vibration occurs due to the earth's, due to anything, earthquake, tsunami, whatever it is, they can actually change. So they connect something with a spring damper, so they can actually change, so that the natural frequency of oscillation will not be close to the actual oscillations of the system. So that type of things. But in electrical engineering, we can easily implement that. We can make the damping close to 1 or more than 1. If it is close to 1, even under damp, like 0.9, 0.8, 0.85, is still okay. But if it is like 0.5, 0.6, system is really, really bad. Okay? So you will have that. But in second order system, there are a few more terms. Not only the time constant. Time constant is not applicable here, but rather we define few other terms. So one is the rise time. Usually is measured between 10% to 90% of the response. And then we measure settling time, which is close to either within 5% band or 2% band or 1% band. So they related to delta omega n. Okay? So you will have delta omega n. So like if you think of settling time based on 5%, you will have 3 by delta omega n. So like that they use. Even though sensor is an element, but you can actually think of as like a control system toolbox. Okay? So you can say it's a black box. I give input, I get output, and I can actually define all those parameters from the relationship between input and output. So when you characterize, you can think your sensor is like a box. So you do not bother what you are actually trying to measure. You can do the experiment, but when you do the experiment, it's one of the important things that your test chamber should be under control, and you should change the parameter one at a time. You understand what I mean? So if you do not have that, environmental parameters can actually change your result such a way that you won't be able to characterize the sensor properly. Okay? Like you define sensitivity, you should have only one parameter change. So unless you make other parameter fixed, it's very difficult to define to see about the characters of the sensor. So you will be able to define all the terms. I mean, not define, you will be able to get all the terms of the sensor if you have that opportunity of doing the characterization. So you can change one at a time from low value to high value, keep that phase constant, change the other, and see the other values, and get the output, and then you can get a set of curves, and you can define each and every one, and also you can define the cross sensitivity. Okay. So another thing which is coming to sensor hysteresis, which may not be so much important but also is required. So suppose you are in a situation where the system is dynamic, it's increasing then decreasing. Now hysteresis is the path we define that when the input is increasing and then input is decreasing, whether it follows the same path. If it does not follow the same path, that means it actually kept some history in its memory, okay? And that is reflected in the output, and that is dangerous. You understand? Because if you have the hysteresis at some particular applications corresponding to 30 degrees centigrade, you got some value, but then when it is decreasing, you get different value. You do not know. You get the value, and that decides the temperature. So if you have the hysteresis at the same value, you don't say it's 30 degree. It may be 32 degree. It may be 33 degree, depending on how much hysteresis. So we also need to do the hysteresis curve. So it's basically you change the input parameters, decrease the input parameters, and see how is the response. So hysteresis is sometimes very, very important. So all these things you can, and bandwidth, it comes to the, when you apply the sinusoidal signal, you can vary the frequency and you see the response. So at some frequency, your response will be constant, and then you see the response start decreasing. Okay? So that's the frequency band within which your response is constant. So that's the bandwidth. Bandwidth is very, very important when you have electronic circuits like op-amp and something like that comes in your circuit. Because if you do not know the bandwidth and you operate at different frequency, you may get completely different result. You understand? Suppose your frequency sensor gives response at 100 kilohertz, but you take an op-amp which actually bandwidth is less than 100 kilohertz. Okay? So you cannot use that. So if you deal with high frequency applications, your instrumentation circuit should have a high bandwidth. The thumb rule is 10 times. Okay? Always you use the thumb rule 10 times. Okay? So that means you operate at 100 kilohertz, your op-amp must have bandwidth 1 megahertz. Sometimes the op-amp, they also give another value called gain bandwidth product. Okay? So usually op-amp means you know that we amplify. If you amplify, your bandwidth reduced, because usually gain bandwidth product is kind of constant. So those are the things you need to be careful of, because you may have your sensor working perfect, but your instrumentation circuit, because of the lack of knowledge or lack of understanding or lack of applications, you get completely different result, and you may blame the sensor, but actually the sensor is very good. So just need to be careful of those terms. Okay, so these are this part actually I know, as I said, I know that most of the things you have studied, so it's just the refresh. So any questions, any comment, please.